In a previous session, we looked at applying the reduction formula method to find the integral of sine to the power of nx dx. Okay, so let's look at cos nx and tan nx quickly. So in is equal to integral of cos nx dx, where n is in the set of positive integers. Now, just like in case of sin nx, we are going to split cos nx into cos to the power of n minus 1 of x times cos x. And now we will use the substitution method. So we'll say u is equal to cos to the power of n minus 1 x. Why cos n to the power of n minus 1 x? Because we know cos x. It is simpler. So let's differentiate this. We get du n minus 1 times cos to the power of n minus 1 x times the derivative of cos x, which is minus sin x dx. So du is equal to this minus, we bring it to the front. So minus times n minus 1 cos to the power of n minus 2 x times sin x dx. Now, if we have taken u as cos to the power of n minus 1 x, our dv will be cos x dx. And integrating this, we get v is equal to sin x. And now we apply the reduction formula. So when we apply that, what do we get? We get u times v. So u is cos to the power of n minus 1 x times v is sin x minus the integral of v du. So v is sin x and du is minus n minus 1 times cos to the power of n minus 2 x times sin x dx. We just keep simplifying this. This remains the same. N minus 1 is a constant. We take it out. Minus times minus plus. So that we have n minus 1 times the integral sine square x times cos to the power of n minus 2 x dx. Now, sine square x, we split it into 1 minus cos square x. And then we distribute this to get n minus 1 times the integral cos to the power of n minus 2 x dx minus n minus 1 times the integral of cos square x times cos to the power of n minus 2 x dx. I sub n is equal to cos to the power of n minus 1 x times sin x plus n minus 1 times the integral cos to the power of n minus 2 x dx minus n minus 1 times the integral of 2 plus n minus 2. So 2 cancel out and we are left with cos nx dx, which is I sub n. We bring n minus 1 times in to the left hand side. We get in plus n minus 1 times I sub n is equal to the rest. In plus n times in minus I sub n. So in and minus in cancel out. We are left with n times in. And now we take the n to the other side. So that we get I sub n is equal to cos to the power of n minus 1 x times sin x divided by n plus n minus 1 by n times the integral cos n minus 2 x dx. So integrating this by again applying the reduction formula, we get I sub n minus 2 is equal to cos to the power of n minus 3 x sin x by n minus 2 plus n minus 3 by n minus 2 times I sub n minus 4. So recursively we keep doing it and keep substituting it. So in I sub n, let's incorporate I sub n minus 2. We get I sub n is equal to cos to the power of n minus 1 x times sin x by n plus n minus 1 by n times the integral of this is this. So cos to the power of n minus 3x times sin x divided by n minus 2 plus n minus 3 by n minus 2 times I sub n minus 4. So opening up this bracket, we get cos to the power of n minus 1 x sin x by n plus n minus 1 times cos to the power of n minus 3 x sin x by n times n minus 2 plus n minus 1 times n minus 3 by n times n minus 2 times I sub n minus 4 and say plus c. Now, actually, we have to keep doing it till when? Till either the numerator becomes 0 or the denominator becomes 0. So, excluding that term, we take whatever we have arrived at. So, if n is odd, the last integral would be, remember cos nx, if we keep subtracting 2 from that odd number, what will happen? If it is odd, we will end up with a power of 1. So integral cos x dx, which is equal to sin x. And if n is even, the last integral would be integral cos to the power of 0 x dx, which is equal to integral of 1 dx, which is equal to x. So that is the integral of cos nx dx using the reduction formula method. Now let's look at tan. Now we have I sub n is equal to integral of tan nx dx, where n is in the set of positive integers. So integral of tan to the power of n minus 2 x times tan square x is sec square x minus 1 dx. So now we have integral tan to the power of n minus 2 x times sec square x dx minus integral of tan to the power of n minus 2 x dx. We have distributed it and split the integral. Let's take the first term and integrate it. Now we do the substitution. U is equal to tan x. So that du is equal to sec square x dx. So integral of tan to the power of n minus 2 x times sec square x dx is equal to, after substitution, integral of u to the power of n minus 2 du, which is equal to u to the power of n minus 2 plus 1 by n minus 2 plus 1, which is equal to u to the power of n minus 1 divided by n minus 1. And substituting back, we get tan to the power of n minus 1 x by n minus 1. So the first term is this. So in is equal to, first term is tan to the power of n minus 1 x by n minus 1. The second term is minus integral of tan n minus 2 x dx, which is nothing but I sub n minus 2. Naturally, which means we have to take care of now I sub n minus 2. So I sub n minus 2 will be equal to tan n minus 3. Remember, we have n minus 1. We are subtracting 2. We get tan to the power of n minus 3 x by n minus 3 minus I sub n minus 4. Substituting I sub n minus 2 to in expression, we get I sub n is equal to tan to the power of n minus 1 x by n minus 1 minus tan to the power of n minus 3 x by n minus 3 minus I sub n minus 4. Now, opening up the bracket, we get tan to the power of n minus 1 x by n minus 1 minus tan to the power of n minus 3 x by n minus 3 plus I sub n minus 4. I sub n minus 4 is equal to tan to the power of n minus 5x by n minus 5 minus I sub n minus 6. So In becomes this expression. And this will keep going till when? Till n minus, as we keep subtracting, we either end up with 0 or we end up with 1. When n is even, we will end up with I sub 0. So that means integral of tan 0 x dx, which is equal to integral of 1 dx, which is equal to x plus c. So if n is even, we end up with, as the last term, x. And when n is odd, we end up with integral of tan x dx, which we know is equal to minus natural log of absolute value of cos x plus c. So that was the integrals of cos nx and tan nx. Similarly, we can do for the rest of the trigonometric functions. If you found this useful, don't forget to like, share, and subscribe. Questions and suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.